As a reminder, the Clausius statement of the Second Law of Thermodynamics states that it is impossible to construct a device which operates on a cycle and produces no other effect than the transfer of heat from a cooler body to a hotter body. This means that some work must be performed to cause heat to flow from a cold body to a hot one, as in a refrigeration cycle. Earlier this year, researchers at the University of Zurich conducted an experiment that appears to break the second law of thermodynamics. They managed to cool a 9-gram piece of copper from over 100 degrees Celsius to below room temperature without an external power supply. Theoretically, this experimental device could turn boiling water to ice without using any energy, says Schilling, the professor at the University of Zurich who led the experiment. However, as we have learned in class, this type of process is impossible. So for our final project, we investigated this process to find out: how did researchers at the University of Zurich cause heat to flow from a cold body to a hot one without putting external work into the system? And consequently, how does this process still comply with the second law of thermodynamics? The experiment produced in Switzerland takes advantage of the large temperature difference between a heated piece of copper and the ambient room temperature with the use of a Peltier element. The Peltier element connects the thermal system to an electrical one to harness the copper's thermal inertia, which can be described as the degree of slowness with which the temperature of a material approaches that of its surroundings.
Peltier elements are constructed by the series alignment of two types of semiconductors in alternating order between two ceramic plates. When a voltage is applied across the two wires of the Peltier element, a DC current flows across the gaps between the semiconductors, creating a temperature difference. This temperature is absorbed by one side of the device, so one side of the element gets warm while the other cools down. This effect also works in reverse, so that a temperature difference across the two sides of the Peltier element can induce a current through the circuit.
As you can see here, we have our setup. First things first, taking the copper out. We have a temperature probe in the water. Right now it's at about 60 degrees Celsius. I'm gonna dry that off so as not to damage any of the parts in the Peltier element. And then now we have a little homemade insulator to try and keep the temperature of the copper the same. Lose as low as possible. Then now, as we hook it up to the Peltier element, which thermal grease has been applied to help with the temperature, you can see that the potential and the current change from zero is being generated due to the change in temperature. This Peltier element, you see here, we have the voltage we're measuring, a resistor, we're measuring the voltage across the resistor hooked up in series with it. We can also measure the current. As you can see here, we're plotting the values out. After we're done recording everything, we can zoom in and show everyone the graphs of what they look like. It's pretty cool to set a setup similar to what they did at the University of Zurich. Except at the University of Zurich, they had an inductor in series with their system. It's an inductor that we don't have here at Dartmouth. It's been very large, very expensive, and it's just not something that we're able to get our hands on right now. But this is just sort of to help the basic understanding to get the point across. And now you can see as Nick goes to take it off.
Oh my God! Oh Jesus!
Yeah. Peltier element, you can see the voltage and the current start dropping back down to zero as the temperature difference between the two plates in the Peltier element starts to reach equilibrium and decrease from where they had been when the copper had been applied.
The temperature difference across the Peltier element will decrease as the copper reaches room temperature. When the current reaches its maximum value, the inductor acts as a wire, but as the temperature difference decreases, so does the voltage across the Peltier element, and thus the induced current. The inductor maintains the flow of current in the same direction for a brief moment after the two temperatures reach equilibrium, thus pushing heat from the cold body to the hot one.
As Nate stated, we cannot perfectly replicate the experiment due to our limited resources at Thayer. Instead, we measured the energy output of the circuit, which was shown to be 5.593 decijoules. We then introduced a DC power supply to push energy back into the circuit. This pulled heat from the side that was previously in contact with the copper block, showing that, after the block reaches room temperature, the energy created by the initial temperature difference can go towards further cooling of the copper block.
Alright, so we calculated the power that we put into the other circuit, and we're going to mimic the effect of the thermal inductor used in the University of Zurich's experiment by running the same amount of power into this circuit, which still includes the Peltier element, the resistor, and now a DC power supply. You should see the temperature start to go down.
This graph from the original experiment in Zurich displays the amount that the various components in the system contribute to the rate of heat flow across the Peltier element. Each line represents the power of each component in the circuit. The blue and black lines represent the two sides of the Peltier element. The red line represents the power of the resistor. The yellow line represents the power of the thermal conductivity between the copper and the Peltier element, and the green line represents the power of the inductor. Note that the heat flow due to thermal conductivity and the inductor go negative, showing that the inductor continues to push energy even after the two surfaces have reached equilibrium, causing the cool body to become cooler. Although this experiment entertains the possibility of heat flow from cold to hot, it does not break the second law of thermodynamics. Understanding how this system obeys the second law depends on the boundaries of the system. In this experiment, there are two separate systems, one electrical, one thermal, and these two systems perform work on each other. The thermal system does work on the electrical system, thus storing some energy in the circuit before it is returned back to the thermal system, causing no addition of work to the combination of the two. According to Schilling, it would be possible in theory to achieve cooling of down to -47 degrees Celsius under the same conditions if the ideal Peltier element, which is yet to be invented, could be used. He says, with this very simple technology, large amounts of hot, solid, liquid, or gaseous materials could be cooled to well below room temperature without any energy consumption. The development of such technology could lead to major improvements in thermoelectric cooling.